Good morning, good evening, good afternoon. Welcome to the MECI Alliance seminar series. In Boston, at least it's a sunny day. Hopefully everybody has a chance to enjoy and relax over the coming long weekend. Today we have with us Dr. Richard Weissman, professor of the practice in the department, an alum of the department, and has a diverse career that sort of is a mix of both technology, so hardcore technical, hardcore financial, and a very sort of elaborate and sort of expansive view on how to be a mechanical engineer in the world. He'll share some projects that he's worked on in the past and share a little bit about his career and the journey that is taking him to continued reinvention and rediscovery of the excitement that it is to be a mechanical engineer. Dr. Weissman, thank you for joining us today. Look forward to hearing about your words of wisdom and your experience, and turn it over to you to amplify your introduction and share your reflections on a career in mechanical engineering.
Well, thanks very much, Brian. Let me go through let me do a few adjustments here. I think we're okay now. Does that look all right to everyone? Good, good.
That's good, coming through.
Thanks very much. As I told Brian, I had sort of a last minute equipment failure and had to move a few things around, but better that the failure occurred then than now. So let me get going on this. As you've already heard, I did my bachelor's and master's and doctoral work all in mechanical engineering right there at MIT. And towards the end of my let me just get up here. Having a little issue here with the presentation mode. There we go. Towards the end of my doctoral thesis work, my funding was running out. So I decided to take on some consulting work. For me, that was a very, very good decision. It gave me a chance to put into practice some of the work I'd been doing in control theory, some of the things I'd learned along the way. I was now able to do some work in design and mechanics and other areas that I had studied. And it was all around a good move for me. One of my first clients was Foster Miller. Now that's a company that was started about a generation before me by three people who came out of the mechanical engineering department at MIT. At Foster Miller, I was literally like a kid in a candy store. I started out working on designs for new mining machines. What could be better for a young engineer than being given lots of energy, as much steel as I wanted, and the ability to develop novel sensing and controls? And I'll talk a bit more about that later. When I did complete my doctoral work shortly after that, I decided to keep my consulting practice going, and I continued the sorts of work that I had been enjoying so much. After a short time, the president of Foster Miller and one of the founders, Dr. Charles Kojabashian, another graduate, of course, too, convinced me to join Foster Miller full-time, and I did. Shortly after I joined, the Department of Defense wanted a new generation of explosive ordnance disposal robots, or EOD robots, as they're called. They needed something that could climb the steepest stairs and maneuver in narrow hallways and doorways and employ a special manipulator arm that could extend quite far and tear down suspended ceilings or reach high objects. They needed things that could carry special EOD tools like de-armors and things that generated high recoil forces. And they needed all sorts of situational awareness tools, special optics and low light cameras and that kind of things. But one of the main needs was modularity. That resulted in one of my first proposals I wrote at Foster Miller. We won the project. It was one of the first programs that I managed there, and it was the beginning of the robotics business at Foster Miller, which I'll get into also later, and we'll show a number of the robots that were developed for both hazardous duty applications and for work in industrial and commercial environments. Also near that time that I joined Foster Miller, the Navy was coming out with requests for proposals to investigate new ways to launch aircraft from carriers. Steam-powered catapults had been the method of choice for many years, and there was interest in investigating electric power as a means for launching these aircraft. Well, it just so happened that my doctoral research was on high-speed linear induction motors for transportation. While my work didn't really consider the particular needs of aircraft launch, um, it did put me in a fairly reasonable position to think about electric machines that could meet the Navy's new needs. Once again, I was out writing proposals and starting to win some programs, which marked the beginning of our work in electric machines and actuator and the start of that whole business area. In late 2004, Foster Miller was acquired by Kinetic. Kinetic was a relatively new company in the UK, and it came about from the privatization of a number of the MOD's facilities and labs and test ranges and other capabilities. At the time of the acquisition, about 35 to 40% of our business was in the defense area, and the rest was in commercial and non-defense government areas, and a very, very wide variety of work, and everything from food processing to medical devices to every sort of industrial process and application you could imagine. I became the CTO and the executive vice president for all of Kinetic North America, which was made up then of a number of companies working in both technology development and supplying engineering services. Shortly after that time, MIT approached me and asked if I might be interested in a professor of the practice appointment. My board at Q&A thought it was a great idea as long as they didn't completely lose me. And after a little discussion, I was able to split my time between Kinetic and MIT. In 2019, I joined Arsenal Capital Partners as a senior advisor and member of their advisory board. Arsenal is a private equity group that deals almost all in technology-based acquisitions, and the acquisitions are in the health sciences area and special industries. I focus most of my efforts on special industries at Arsenal. And finally, late last year, I decided to take on some new challenges. I decided to leave Kinetic, the company I had spent 40 years helping to build, and I later joined General Atomics, a company that I had worked with for many years, and I am helping to open General Atomics' first office right now in the Boston area. One of the most common questions that students ask me relates to, whoops, I am so sorry about this, relates to what many believe is a necessary career choice between staying technical or moving into management. The simple answer is that as a mechanical engineer, you may not need to make that choice. If you want to move into management and focus on that, you certainly can. If you want to remain technical, you can do that. And in many cases, you can do both, or you may need to do both. In my case, I found I needed to do both. And fortunately, I also discovered that I like doing both. Mechanical engineering prepares one to investigate and understand systems and subsystems and components and their behaviors. And I like to divide the engineer's mission into the major task areas that you see below. Investigate's pretty self-explanatory. In understanding, I'm talking about understanding behaviors, the performance of systems and components, and defining the desired changes or the new systems that you desire to create. These definitions almost always include performance parameters, but they almost always need to include cost, and frequently they need to take into account the payback that certain customers need to see for the system to be viable. Development includes developing modifications, upgrades, corrections, or entirely new systems and components that have to perform in the manner that you've defined as being desired. And finally, the implementation, which begins with testing, verification, and validation of the new creation. The system domains may include mechanical, electrical and electronic, fluidic, thermodynamic, biological, or just about anything else. The applications can be in a very broad range of things, including transportation and health and medicine and structures and energy and agriculture and food, energy generation and distribution, consumer products, textiles, defense and aerospace, and on and on. Another important thing to note is that a career in mechanical engineering can branch into other professions. I've had a number of friends and colleagues and students over the years who have very successfully branched into other professions, with mechanical engineering being their base. And I'm including professions like medicine and law and finance and defense and other areas. why does it seem to work out so well? Well, many of these other professions require at least elements of the same ability to analyze a system or analyze a component. They require the same abilities to understand system behaviors and system characteristics, to define the desired behavior, the characteristics or outcome that's desired, to develop and implement a strategy or modifications to obtain those desired behaviors and characteristics, and finally, to test and verify the new system behavior and performance. So it's not at all a limiting profession. It's a profession that, if you desire, can be used as a very logical and useful stepping stone into other professions. I got to give you one quick example. The first time I was on jury duty, which is a very interesting thing to do. If none of you have had that opportunity, I recommend it. After the first day, the judge asked if he could talk to me afterwards. You know, they have you fill out a little bit of a resume as part of jury duty. And he said, you know, I saw you're a mechanical engineer. And he wanted to tell me that he started out as a mechanical engineer. And then he got interested in intellectual property law and went into that. And one thing led to another, and he was now a judge. So that was a great example of how mechanical engineering served to branch into another profession in a very logical way. As I mentioned, some of my earliest professional consulting work was with heavy machinery and mining equipment. Could there be a better area for a new mechanical engineer to start their career? With heavy machinery and lots of power and energy and challenges in mechanical design and controls and materials. And it was kind of amusing to me that in that business, steel plates up to 1 inch thick were referred to as sheet metal. So it was kind of a fun way to start out, and an interesting one. Some of the objectives of my early work in mining equipment design and development included improving the overall machine processes and productivity, more effective material removal using less energy, adding sensors and computers, which were pretty new, embedded computers at the time, for better control and better performance. A big part of it was improving the health and safety of the human operators, moving them away from maybe the hazardous mining phase to safer locations. And a big part of all this was being able to implement some of the early and powerful microcontrollers, but implement those in a reliable manner in what were often very wet, explosive, and high vibration and shock environments. There were some lessons learned in that early consulting, and they were important lessons I'd like to pass along. First, without careful management, and this is if you can't take on pure technical roles, and it tends to require program management in anything but sort of the smallest, most narrowly defined tasks. You find that schedules will quickly get out of hand if they aren't carefully managed. You also find that in general, costs require careful management, and part of the big part of the program management to keep costs under control. I often tell my students, and I mean this seriously, you start out with a mechanical design that may seem to have generous margins for power and energy available, but I almost always find that those margins get eaten up through both unanticipated losses and through unanticipated new needs for consumption of energy that comes into play. So I often like to say you never seem to have enough power and energy available on these designs by the time you get to the end. Finally, customer feedback. Validation testing of mechanical hardware can be a very, very humbling experience. And I'm sure a few of you are nodding out there. Hardware can be very, very humbling. Users and customers need to provide feedback, and they generally will provide feedback. It's good to have a thick skin, to keep an open mind during these stages of a program, because after all, a project is only as good as the market acceptance that it will be able to gain. As I mentioned before, I wanted to show some examples of two of the specific business areas that I was fortunate enough to be able to found at Kinetic and Foster Miller. The first one deals in special electric machines and actuators. And we've done a number of those over the years. Some were very small, some were very large, some were to work in very hazardous environments. And I'm really quite proud of that business area and the work we did. But as I mentioned, it started out with what I learned in my doctoral thesis. It led me to one of the longest projects of my career and one of the most interesting. My doctoral thesis was called Experimental and Analytical Characteristics of Linear Induction Motors for Transportation. To start off, let's talk a bit about some of the fundamentals of induction motors and what is a linear induction motor. So if you can live with my rather crude sketches here, which are actually things I took out of my thesis, here's what might look like a cross-section of a very conventional squirrel cage induction motor. And these motors comprise the great majority of all electric motor horsepower in use today. And the reason is that they are so rugged and so simple. So you have a stator, an iron stator with teeth on the outside, multi-phase windings that rest within those teeth. When they're energized at a given frequency, they produce a moving magnetomotive force wave that passes around it, depending on the winding configuration and the speed. And then on the inside, you've got an iron rotor with these sort of embedded conductors. They can be copper. To save money, they can be aluminum. And this is often called a squirrel cage rotor because it has that look of little bars. If we take that and start cutting it and unwrapping it, as I've tried to show here, you can see how you can transition to a rotary version of the same motor with the stator, or what we call the primary, on the bottom, and this what was the squirrel cage, or the secondary, with those conductors on the top. The beauty point in the induction motors, one of them is that they're made with very simple materials. There are no brushes, there are no permanent magnets, there are no rare earth materials. They're very simple, rugged materials. And one of the issues with what we're looking at here, of course, is that we can't go very far with this. This can give us some linear motion and force, whereas we had torque and rotary motion here, but we aren't going to get very far with the motor shown there. For the work in my my thesis, I was looking at transportation applications. So I was looking at the short primary here, which might be the train, moving along a track that would be a continuous secondary. So here we've also made a transition for this so-called single-sided linear induction motor to a secondary where the squirrel cage bars are gone and we've got a sheet conductor here. Typically it'd be aluminum to save money, just as going to the sheet conductor instead of the squirrel cage is a cost-saving thing, because this is the track that will go on a very, very long distance. The penalty we pay for going to a sheet conductor is basically the air gap gets bigger. So we've got a forced flux over a much larger air gap, whereas before the air gap went from the iron tooth to the top of the iron of the embedded conductor. Now it goes all the way to the back iron, you can see here. Let's talk about a couple of variants of the short primary and short secondary slims here. So here you see simply a short primary, as we just talked about, moving along what could be a very long secondary, or we can go the other way for particular applications and have a much longer primary with the actively powered windings and the passive short secondary moving along that. Here's three interesting examples, and I think this will start to point out why this looked like a good way to go, and proved out to be a good way to go for the aircraft launching problem. So here we see the short primary and the long secondary with a sheet secondary conductor. Now here we see the primary, we've detached the back iron from the secondary, so it can remain stationary and in line with the primary. And only the conducting sheet, which could be fairly low mass aluminum, now is moving with respect to the primary. You can see that we've got a little bit bigger air gap, but we've still got iron on both ends to complete the magnetic path here, and that helps. And why might one only want the sheet conductor to be moving, the low mass end to move? Well, think about the application for launching aircraft. We've got to accelerate and ramp up pretty fast. And then in a much shorter distance, we've got to bring that motor to a halt. So it's kind of nice to have a very, very low mass moving item at the end there where you have to bring it to a halt. Down here, for certain special applications, we're willing to get rid of the back iron altogether. And the problem here is that we're paying the price for having the flux, a very high reluctance path here, and moving so much of the flux through air here. Now, let's just talk a bit about the characteristics of an induction motor and why they weren't particularly popular for use in applications where one needed to carefully control force or speed. So here's a typical torque speed curve for a typical induction motor. At stall speed, you've got the most slip between the non-moving rotor and the moving magnetomotor force. So that's the torque that's generated at 0 speed. It peaks to a high torque, often called the breakover torque. Down here at synchronous speed, of course, no torque is generated because the rotor would be moving at exactly the same speed, moving with the magnetomotor force waves, so no currents can be excited in that moving rotor. And most of these applications all over the world that we're using big induction motors are kind of working in this region. So for a 60 hertz driven machine in North America, a typical synchronous speed might be 1800 RPM, depending on the winding configuration. And you'd have a lot of these motors driving big fans or pumps or compressors kind of working in this region, maybe 1700 to 1750. If that motor took on a slightly higher load, it would slow down a bit and the torque would come up to match the load. If the load dropped off, it would speed up a bit. And this would sort of be the typical working region. So they're great workhorse motors, very, very rugged, relatively inexpensive for applications where you didn't have sort of critical control requirements over speed, where the speed could droop a bit or pick up a bit, and where you just didn't have that controllability. Now, what happens if I start to excite this with different frequencies, if I could generate different frequencies? Well, what happens is for every new frequency, I get another torque speed curve. So I generate over a range of frequencies an entire family of new torque speed curves, these nonlinear curves. So you can see that the control process can seem to get a bit complex as compared to controlling a synchronous permanent magnet machine or a separately excited synchronous machine. So what was the Navy looking for at the time? Well, they were looking for smoother acceleration that would put lower stresses on the airframe. They were looking for, they were looking for capabilities to reject disturbances. They wanted to have true closed loop control. What kind of disturbances would you see on a flight deck? Well, you could see motions of the ship, waves breaking, wind, jet blast from adjacent aircrafts, all of those things. So they wanted closed loop control and the rejection of disturbances. Lower life cycle costs, a big issue. Carriers are built typically for a 50-year life or greater, and this equipment had a long time, a lot of use. So anything you could do to reduce the regular costs of maintenance and operation of that would be greatly expanded over the life of that system. They wanted the ability to go to heavier, larger, and faster payloads and smaller, lighter craft like unmanned aircraft. And finally, they wanted overall improvement in the ship architecture, better weight distribution, less distribution of high pressure steam systems, which of course can be very hazardous and very, very heavy. And the question was, could a linear electric machine be the answer? Well, once again, I was back writing proposals with a group of folks. We started writing proposals, and after a number of successful programs in which we demonstrated linear induction motor-based designs and control those designs, Foster Miller teamed with General Atomics, and we went on to win the Electromagnetic Aircraft Launch System, or EMALS design and development contract, and we also went on to win the Advanced Arresting Gear, or AAG design and development contract. Today, General Atomics remains the prime contractor for these systems on new U.S. Navy carriers, and Kinetic, formerly Foster Miller, remains an important contributing partner. I just wanted to say a word about what some of these programs look like that we started off doing, and one was called the Electromagnetic Aircraft Arresting System, or EARS, which you see here. As you've all may have seen or watched movies like Top Gun or other things, the way these aircraft come in for a landing on a carrier is they have a hook that drops down in the back of the aircraft, and they hook one of typically 3 cable pendants draped across the flight deck. Those cables are reeved below the deck to systems that provide braking and damping of that energy to bring the aircraft to a halt. Here you see a system we built where we used linear induction motors on either side to control the braking on the sides of the pendant. In this case, we're firing about a 200-pound scale model aircraft out of an air cannon at different speeds, at different angles, and at different offsets. And what we know about arrestment is that there is a place on the flight deck we want that aircraft to come to a halt. We don't know exactly which pendant will be caught before it happens. We don't know the exact trajectory and the exact velocity of that aircraft until it occurs. And we don't even know the exact mass. We do know where we want it to come to a halt. We want to bring it to a halt there with the minimum amount of forces placed on the airframe. If we undershoot that point, we've probably put some excessive stresses on the aircraft. If we overshoot that point, we may get into some other problems. Programs like this, where we demonstrated the performance and the controllability of these linear induction motors, fed directly into the Navy's Advanced Linear Motor ALM program, and that fed directly into the Electromagnetic Aircraft Launch System, or EMALS, which, by the way, is a Phase 3 SBIR program, and to the Advanced Arresting Gear, or AAG program today. A couple of things about what's gained by EMALS and AAG. Well, increased capability, launch weights that are higher, greater margins, lower life cycle costs, much higher availability and reliability, which translates to greater safety, better compatibility for the more electric ships that are demanding more and more electric power for communications and other activities. Very consistent performance, goes back to that closed loop control. System readiness and responsiveness, ready to launch in a matter of minutes instead of sometimes a matter of hours that steam systems can require from a cold start. Improved energy efficiency, order of magnitude improvement in the launch efficiency. Reduced requirements for certain ship auxiliaries. For instance, 37,000 gallons of water are saved per operational day. Improved shipboard quality of life, a much quieter system, and an overall ease of operation and maintenance. We're talking in general about changing out electronics and boards as opposed to doing work on heavy steam systems. Today, over 7,000 launches have been completed. That may be a much higher number now, in fact. The controllability has been excellent. It's been a 100% safety record, and testing has gone on in operation in all sorts of weather conditions. I want to go on now with a very quick video. It should be under 2 minutes. And now I wanted to move into the other area that I mentioned I'd be talking about, and that's mobile and specialized robotics and unmanned systems. The other business area I was fortunate enough to get into and help to found and develop at Foster Miller and at Kinetic today. This includes a variety of different systems. I'm going to show you a number of teleoperated and semi-autonomous machines that replace humans in hostile and hazardous environments. Some of these environments are handling explosive materials, some are high radiation environments. Some of the machines we've done over the years are working in other potential hazards like conditions that can become flooded suddenly. Some of these are machines that simply access areas, areas that humans cannot get into, underground pipelines, underground power conduits, overhead high voltage transmission lines, or even caves or tunnels that are too small or represent other hazardous issues. Some are examples of robots that can perform certain operations with greater accuracy and reliability. Things like rapid identification and classification of items, sorting and packaging, neutralization of hazardous devices, and of course, even though I'm not going to show any of these, devices that perform various medical procedures. And in many cases, particularly in some of these commercial environments, they're robots that are replacing a declining labor pool because of changes in the North American economy. They're working in areas that people simply choose not to work into, not to go to work in. And the labor pools are declining, and there were other things needed to replace that. The first project that started it all was the Ramrod, or Ferret, which was the civil version of the explosive ordnance robot, Ramrod being the system developed for the Department of Defense. Ramrod stood for Remotely Actuated Mobile Platform for Render Safer Disposal. It was a procurement out of the NavEOD Tech Center in Indian Head, Maryland, which for many years handled all of the development of EOD equipment and robots for all of the Department of Defense. As I mentioned before, the system had to be highly mobile, climb stairs, had to work on really tough surfaces like sand and mud, had to have this long reach manipulator, which telescopes. In this case, we chose to go to a telescoping manipulator that goes from 3 feet to 11 feet. Had to be capable of supporting 200 pounds plus at full extension and being able to tear down suspended ceilings for inspection. Using cameras that had pan and tilt and zoom optics and lighting. The cameras are going to look kind of large in this, but that was the state of the art back at the time. And a driving camera that you can see down below that had low light capability. And other sensors like two-way audio to be able to listen to things or be able to send messages out. The system had to be highly modular. You can see an example of it here, where the camera pan and tilt's being moved from a stationary position on the robot out to the end of the arm. In that previous picture, you might have noticed the end effector. Was a high force clamping end effector, which had 1,000 pounds of gripping force on parallel jaws and 1,000 pounds of continuous roll torque in either direction. That was designed for our customers that wanted to be able to disassemble 4-inch pipe bombs. So it was the capability of that for forensic work to be able to attempt to remotely disassemble these pipe bombs. It had as a large capacity end effector. This one made for capturing very odd shaped large boxes and other items. And then there's a very small end effector with a compliant centerless wrist. And that was used to hold keys, even car keys that it could gently insert into car door locks or trunks to open them, or for grasping small locker handles and opening those. And you can see the pan and tilt up there. It also carries a couple of different types of door stops on the rear. So it could stop a door that it had gone through and keep it from closing behind it. And it had to be compatible with a variety of EOD tools. Here you can see this manipulator arm can unlatch with just 4 quick latches and be taken off in a matter of seconds and replaced by various other EOD tools. This was a photo to show the 5-stage telescoping stainless steel arm. Without the end effector, this arm weighs only 66 pounds with its actuating motor. And here you can see that at full extension, it's lifting the front of the robot, which weighs in at about 430, 440 in this configuration. Finally, the ferret actually became a TV star for a while. And you can all Google this and see an old show that NBC had called True Blue, which was a show about the emergency services unit, the New York Police Department. They had purchased and used a number of the ferrets for hazardous operations and hazardous material handling. And this got picked up on, and one of our ferrets became a TV star. They gave it a name, Sammy. I'm not sure why. And today, Sammy is retired and resting in my office at MIT. So after we get through the pandemic, if somebody wants to come and visit Sammy, and some of you have probably already seen Sammy around, and a number of students over the years have used it to explore the way the mechanisms and the drives and the way things were fabricated and that sort of thing. Moving on to some other EOD and hazardous duty robots that came out of Foster Miller and Kinetic. This is the real workhorse. This is the Talon. There have been over 4,000, close to 5,000 Talons fielded worldwide. And while I didn't have much to do with any of the technical development of Talon, you can see that much of it is a very natural outgrowth of a lot of the mechanisms that were in the larger Ramrod and Ferret systems. High degree of modularity, many special cameras and sensors, a variety of different manipulator arms and end effectors, and different EOD tools can be used. We're quite certain that Talon over the years has saved many, many lives and prevented many, many serious injuries by taking the place of a human in hazardous environments. Talon is equally capable of handling very, very rough terrains and settings. As I said, a variety of end effectors and approaching a variety of objects and payloads. One of the other great points about Talon is that even though these devices frequently get damaged and sometimes heavily damaged in the field, doing exactly what they're supposed to be used for, as teleoperators, taking the place or providing that longer reach for the human operators, Talon is remarkably good at being field repaired and rapidly repaired. Often in a matter of minutes or sometimes a few hours, you could have one completely back and running and supplying that important capability. Here's another very small device, the Dragon Runner from Kinetic Foster Miller. Obviously something much smaller, something that can be easily picked up and carried. Very, very good, and again, sold throughout the world. Very, very good at poking around and doing surveillance and employing light manipulators for picking things up or looking around at things. And another powerful tool. Again, one that I didn't have any direct input on the technical design, but an important product I wanted to point out. And finally, the newest is the Spur, or Squad Packable Utility Robot. This is a very, very new system, quite small, and you'll see some photos of it. Highly, highly modular, employing a wide variety of cameras for driving, for looking around, a wide variety of specialized optics, manipulators, end effectors, and other tools on board. Here you can see one on extremely, extremely steep stairs, and that gives you an idea. Spur is highly mobile. It's able to scamper up. I can't even call these stairs, but that gives you an idea of how small it is. I did direct much of the design of this robot. It's a clean sheet design that I'm very, very proud of. It was derived through processes and iterations of ideation, modeling, and analysis and testing. And I need to point out, these are pretty much the very same processes that are taught in Dave Wallace's 2009 class. So to any of you students that have 2009 coming up, to any of you alums that took 2009, I can guarantee that everything you're learning in that class is very, very much applicable to professional practices that you might get into beyond MIT. I also want to point out that Spur was the winner of the Department of Defense Common Robotic System Individual Program of Record. That was a very, very significant competition for a program that will potentially be fielding thousands of these robots. Here you can see, again, even though it's very, very small, it's able to traverse mud and water and sand and handle very, very tough terrains and rocks and obstacles. And while handling these, it's able to also grasp and carry fairly large and fairly heavy payloads. Spur's a real transformer in the end, and this is part of the mobility. Here in literally seconds, it folds down to a very, very small flat pack. For those of you that might be familiar, this is a MOLLE 2 pack. Let me just say, if you aren't familiar with this size pack, this is much smaller than the backpacks that most students are carrying around MIT. So it truly is backpackable. It truly is, it can fold down without tools. In a matter of seconds, you can do this by hand very, very easily. You could do it in the dark if you were even slightly familiar with it. So those were important aspects of the Spur that I and Kinetic are really quite proud of, and promises to continue the tradition of helping to save lives and prevent injuries and to do valuable work in intelligence, surveillance, and reconnaissance. Here's an interesting robot, much bigger, that MIT was part of the development team, the shipboard weapons loader. Here's the problem before we get into the shipboard weapons loader. Loading fuel pods and payloads and weapons on a flight deck, which may be in day or night conditions, maybe rough weather, maybe cold, maybe hot. And a lot of these operations are largely carried out by hand, with lots of people helping to lift and position these devices in what may be a pretty tough environment. So you can see what's going on here. The answer to this was the shipboard weapons loader. Here's a laboratory prototype. And you can see the size of it here. It's a true cobotic system, which amplifies and provides safe holding for the operator. MIT did the admittance controls that prevents the system from jamming up some of these payloads as they're loaded or doing any damage. This is a 7 degree of freedom all electric manipulator because hydraulics are not permitted in some of the environments it operates. It has a 3,000 pound capacity. And for comparison's sake, if you had a similarly sized industrial manipulator, it might have more of a 300 to 500 pound capacity at the same size. It operates with omnidirectional wheels, so it can rotate in place, squirm left, squirm right, go forward or backward, position itself going over chains and cables on the flight deck. So very, very mobile, very, very useful tool. Moving into commercial space again, this is called the box handler robot. It's made to work in flow-through storage facilities, which is by far the most common warehousing facility. And I'm sorry, in this picture, it happens to show a facility with no boxes or pallets present. But what happens is boxes come in this case, 2 different size boxes on a conveyor. Labels get read by the robot, or if there's human operators, by human operators. The boxes get carried over to the right bins, stacked on the pallets. When the pallets are full, they're released and they gently roll down to the other side of the storage system, which is called the picking side, where the opposite takes place. To fill orders, these boxes get picked off of the other side of the storage facility. They go onto conveyors and go out for transportation or whatever's required to fill the orders. The system had to be retrofittable in existing facilities. There's a lot of capital investment in these facilities, and we couldn't start over by trying to build fully automated facilities. It will handle multiple boxes, up to 4 or 5, depending on the size at one time. It will, again, we could not use any hydraulics because it was working in a food storage facility. It was integrated with complete inventory tracking for every box. Had to function as a distributed control system with supervisory control over semi-autonomously functioning box handling robots. Finally, I wanted to point out the LiDARs, and there's another one located at the other end you can't see. So this could function in a warehouse with humans working maybe in other aisles or walking around. Whenever an obstacle or human would come into a certain range, the robot would begin to slow down. As that range got tighter and tighter, it would come all the way to a stop for safe operations around people. Here is another one called the RoboPacker. Oh, and by the way, that box handler was directly addressing the problem of a workforce that simply was disappearing. So it needed to fill in for people that they simply couldn't get anymore for those activities. The box RoboPacker was doing much the same thing. Again, this was working in the food type business. It's handling over 120 different agricultural products. So the products it was handling were varying in size and weight slightly. It had to come in and weigh each product, identify what the product was. You see 2 stations here. It could handle up to 2 different sizes of boxes. Can't see the robot manipulator over here, but it used a very sort of squishy air bladder type end effector, so it could very gently grasp these products and not damage anything. Some of the boxes were to be packed by a piece count strategy. Some were to be packed by a weight optimization, so it was weighing and identifying and counting all the time. And this was being used in a food plant that had to be compatible with wash down every 16 hours using high pressure water and caustics and that sort of thing. And again, it was performing in some cases an operation more efficiently with fewer errors than humans, but most importantly, it was taking the place of a workforce that was rapidly disappearing. And the final robot I want to show you very, very quickly, I promise, will be the Pipe Mouse, which is a truly autonomous robot. You can look up the patent yourself. It is a fundamental patent that's almost always cited by other patents now that for internal pipe inspection. It was sponsored by the Gas Research Institute. It was designed to work in 4 to 6 inch nominal pipe sizes. And if we consider all the materials it had to work in, that's 3.1 to 6.4 inch IDs, handling all the fittings, blocking no more than 50% of the live gas lines at any point in time, having to work in what may be flooded areas and old cast iron piping. And it was sending continuous video transmission and receiving high level commands through a fiber optic tether that was paid out. Other robotic inspection devices are typically sort of heavy tractors that drag tethers into the pipe. They're usually limited by the friction of that tether, and the capstan equation will rear its ugly head if you try to go around more than a couple of elbows. It will quickly bring it to a halt through the friction from going around the corners. That's why the Pipe Mouse carries 2,200 feet of optical fiber, pays it out under almost zero tension, and picks it up as it retraces its steps, cleaning that fiber off and reeling it back in. The inspection capabilities included things like looking for dents or ovality in the pipe, which would indicate external third-party damage, which is the most common reason for pipeline failure. Looking for any obstructions or collapses, and being able to use things like magnetic flux leakage, ultrasonics, or eddy currents, depending on the material, to look for cracks or gouges or wall thinning or pitting in the pipes. I'm going to go quickly here. It would carry lithium thionyl chloride primary battery pack for 8 hours of operation. Typical traveling speeds were 5 to 10 feet per minute, and had to traverse any of the fittings that one might encounter. Here's a picture of one of the laboratory prototypes. This is a tractor or locomotive at either end, and then we would string cars in the middle, this being the minimum configuration. The fiber optic winder car is here, with a housing that pays the fiber optics out to the rear, and the battery car is here. And here you can see a drawing from the patent showing 4 cars strung in between. Here's a close-up of one of the tractors that I talked about, and pay particular attention to these links we called curling links at 16. These generated a curling torque on the tractor, so it's trying to force this front lead wheel downward. That's how we designed the device to steer in this very, very rough, disordered environment. So if this was rolling along in this configuration and there was an opening, a T or an elbow going downward, it would take that downward trend. If we didn't want to take that downward trend in a T and wanted to go straight, we would roll the robot over so it's gripping at the 3 o'clock and 9 o'clock positions, and it would pass right through the fitting. Here's quick pictures of those 3-wheel triads in the minimum diameter configuration and the maximum diameter. And how do we roll in the pipe? How do we steer to selectively a line to take turns or not take them, you can see that each of the wheels would turn. So at 45 degrees here, it would corkscrew down the pipe. If we had to turn very quickly or roll very quickly, we could go to full 90, come to a stop, go to 90 degrees and roll in place in the pipe. Or for taking a straight path down the pipe, we could have the wheels in the usual configuration. The pipe is clamped with actuators that have controlled closed loop control clamping of the pipe force. The pipe mouth senses whether it's slipping or not. If it's slipping, it clamps tighter. It's continually sampling the pipe force to see if it can lighten up the clamping force to preserve energy and keep moving with a lower and lower force. And here we can finally see it negotiating a concentric reducer going from the largest diameter down to the smallest diameter. And here going through a zero radius square corner inside elbow of the narrowest inside diameter pipe. And you can see the kinematics and the motions it goes through are simply too complex to ever do this in a teleoperated manner. So that's why it had to be truly autonomous with just a high level of guidance from the operator. So finally, I realize I've gone on a bit long. I just in summary wanted to say to any of the students or any of the recent graduates or any of the not so recent mechanical engineering graduates out there, I believe you selected an absolutely wonderful career. You can stay technical, you can transition to management if you want, you can do both. I'm living proof of that. Virtually every project, however, other than the smallest, pure little technical, narrowly defined projects, will require careful program management to ensure that you're meeting all of the performance goals, the cost goals, and the schedule goals. And with that, I will turn it back to Brian. Thank you.
Rich, thank you very much. I send you the virtual and the physical clapping here. So thank you for sharing that wealth of information and exciting engineering work. We have a number of questions. I know we don't have time for many of them, but if I distill one of them, I think there were a number of questions here, Rich, on the sort of the balance and the decision making between pursuing a career in academia, going the faculty track versus going into work at a national lab or a company. Just the students here were asking your perspective on sort of the trade-offs between the two, having yourself sort of come back to academia after a career in industry.
Well, certainly, I think some time in academia and the ability to win research projects and supervise research projects allows me to get into sort of a deeper investigation of technical elements and get into fundamental research. I find that more of what I've done in industry is applied research, of course, than fundamental research. So it's a great balance. The other thing, quite frankly, is the ability to hopefully bring some of the experience I've had. I've been very, very fortunate in this career. I've been able to work on so many different areas, and I've only shown you a couple of them. I've been able to go all over the world, and really the experience has just been fantastic, and be able to bring maybe some of the value of that experience back to our students and use that to help them gain new perspectives, to help them with things that may be designs that they're doing in many different sort of application areas or technical areas, and bring some of that experience back. Is that a helpful answer?
Oh, very good. Thank you for that. And participants, please, I encourage you to reach out to Dr. Weissman directly. And if you have additional questions for follow-up, we're recognizing the hour here and do need to wrap up. Rich, thank you very much again. Irina, if you can bring up the closing slide, excellent. So Rich, again, thank you, and everybody, thank you for joining us today. Join us in 2 weeks, Wednesday, April 28th, for the next MECI Alliance seminar speaker. Professor Gallant will be speaking about moving beyond lithium-ion batteries in electric transportation. The MECI Alliance, these Wednesday sessions are our opportunity to engage the community, our faculty, our students, our collaborators. So if you have a nomination yourself or somebody that you'd like to hear from, send us a note. Send it to mekialliance@mit.edu, and we'll work with them and work with you to invite the speakers for the community conversations that you would like to have. So everybody, thank you. Have a safe day. And Dr. Weissman, again, thank you for your time, and see everybody here in 2 weeks. Thank you.